So in this video, we're going to have a look at using stoichiometry, but with solutions. So the first thing that we're going to start out with for solution stoichiometry is we are going to start out with a solid potassium chloride. We're just going to use potassium chloride as our example. And we want to be able to write a reaction that shows what happens to potassium chloride when it is dissolved in water. So we're going to dissolve it in water. So we know that potassium chloride solid is soluble in water. And the reason we know that is because we would check it on our solubility table. And so we already learned how to read that. And so when potassium chloride dissolves in water, it's going to break apart and form potassium ions that are aqueous, dissolved in the water, and chloride ions that are aqueous, dissolved in the water. Okay, now you'll notice that when we take that potassium chloride and we dissolve it in water, we don't include water as part of that reaction because water is not changing as part of the reaction. It's still H2O at the beginning, it's still H2O at the end. And so we know it's dissolved in water because of these aqueous states. And so we know that that is potassium ion that's dissolved in water and chloride ion that's dissolved in water. Now, if we use a more complicated solid, so say we use a solid like, let's do aluminum sulfate. So if we do aluminum sulfate is Al2 SO4 3. And when we dissolve aluminum sulfate in water, we're going to produce aluminum ions, which have a 3+ charge, and they're going to be aqueous. And we're going to produce sulfate ions, which have a 2- charge, and they are aqueous. But then we also have to go through and balance it. So we're going to actually produce 2 aluminum ions, and we're going to produce 3 sulfate ions. Okay, so that aluminum sulfate, when we dissolve it in water, is going to produce 2 aluminum 3+ ions and 3 sulfate 2- ions. Okay, and we're just breaking apart our ionic compounds into the ions that created them in the first place. Okay, then we're going through and we're balancing so that we have a balanced reaction here. Remember, we can't do anything without a balanced reaction. All right, so if we use our aluminum sulfate and we have this dissolved in water, another way to say that is that the aluminum sulfate is dissociated. So that's just a new kind of term. So it's dissociated in water. So that means that our ionic compound has turned into its ions, the ions that it originally created. Okay, so if we go back to the potassium chloride, we're going to do an example with potassium chloride, and we're going to start to use this stoichiometry, but in solutions. So if we go back to our potassium chloride, remember our potassium chloride solid turned into a potassium ion that was aqueous and a chloride ion that was aqueous. Okay, now if we dissolved 19.8 grams of potassium chloride in 100 milliliters of water, okay, I want to calculate the concentration of my potassium ion and the concentration of my chloride ion. So remember that those square brackets mean concentration, okay? And a quick side note, of course, some of you may have heard this from me before, but those square brackets actually should only be called brackets because the rounded ones are parentheses, not brackets. But unfortunately, everybody calls the rounded ones brackets, and so we have to use the term square brackets. Okay, so we're using those square brackets rather than the parentheses, the rounded brackets. All right, So if we dissolve 19.8 grams of potassium chloride in 100 milliliters of water, we want to calculate the concentration of potassium ion and the concentration of chloride ion. So the first thing we're going to need to do is to calculate the concentration of the potassium chloride, because we have 19.8 grams of potassium chloride. And that's the most important thing in these kinds of questions, is that your mass is for the whole ionic compound, not just one of the ions or the other, but the entire ionic compound. So our concentration of potassium chloride, we're first going to have to go from the mass into moles. So we want to find the moles for potassium chloride. So we're going to use our 19.8 grams of potassium chloride, and we're going to convert that into moles. So 1 mole of potassium chloride is 74.55 grams. And that, again, is just our molar mass. And so that's going to give us 0.266 moles. And remember, that's potassium chloride. Okay? So then if we want the concentration of potassium chloride, remember, concentration is moles divided by volume. And so that's going to be our 0.266 moles. And our volume, remember, our volume has to be in liters, so it'll be 0.100 liters. And so that's going to give us a concentration of 2.66 moles per liter, and that's for potassium chloride. Okay? Now, where this stoichiometry comes into effect is when we look at, let's go back to our reaction here, and we look at the ratio of potassium chloride to potassium ion to chloride ion, we'll notice that it's 1 to 1 to 1. Okay, so using our idea of stoichiometry, we know that if we had 1 mole of potassium chloride, we would have produced 1 mole of potassium ion and 1 mole of chloride ion. Okay, because they're 1 to 1 to 1. And so we can actually use stoichiometry not just with the mole value, but also with anything that includes moles as the unit, which means we can use it with concentrations as well. So if the concentration of potassium chloride is 2.66 moles per liter, then so is the concentration of potassium ion, and so is the concentration of the chloride ion. And that's because they are 1 to 1 in our reaction. Okay, so in our reaction, they have a 1 to 1 mole ratio. Now, let's see what happens if we use our aluminum sulfate. So let's go back and using the aluminum sulfate. So we know that that solid is going to break apart into those aluminum ions and our sulfate ions. And we knew that we balanced it out with a 2 in front of our aluminum ions, maybe, and a 3 in front of our sulfate ions. Okay, so if we start out with, you know what, let's use 19.8 grams as well. So if we have 19.8 grams of our aluminum sulfate, let's try writing that aluminum sulfate one more time. And we dissolve in, let's go with 250 milliliters this time. And I want to find the concentration of aluminum ion and the concentration of the sulfate ion. All right. So the first thing we need to do is to find the moles for aluminum sulfate. So I have the mass here, and that mass is for aluminum sulfate. So I have 19.8 grams of Al2SO4 3. And so I'm going to multiply that by the fact that 1 mole of that aluminum sulfate's molar mass is 342.14 grams per 1 mole of aluminum sulfate. And remember, when we're calculating that molar mass, there are 2 aluminums, there are 3 sulfurs, and there are 12 oxygens in that formula. Okay, so just as an aside there for molar mass, there's 2 aluminums, plus there's 3 sulfurs, plus there are 12 oxygens. Okay, so we have to use that when we're calculating our molar mass, and that gives us that molar mass of the 342.14 grams per 1 mole of aluminum sulfate. And so when we do that calculation, our 19.8 grams divided by our 342.14 is going to give us 0.0579 moles. And that's moles of aluminum sulfate. Okay, so then if we want the concentration of aluminum sulfate, we're going to do our moles, 0.0579, divided by our volume, which we have to put in liters, so 0.250 liters. And so that's going to give us a concentration of 0.232. Let's try that one more time here. And that's going to be in moles per liter, okay? And again, that's for aluminum sulfate. Now, if we want the concentration of aluminum ions, we have to think about our mole ratio. So, if we go back to our reaction, our mole ratio, let's maybe just do this in blue. 1 aluminum sulfate is going to produce 2 aluminum ions. Okay, so if we have our original value here of 0.232 molar Al2SO4 3, we're going to multiply by our mole ratio. On the bottom here, we need our 1 mole of aluminum sulfate. And on the top here, we're going to have our 2 moles of aluminum ion. Okay, so that means the concentration of the aluminum ion is going to be 0.464 moles per liter. So that's concentration of the aluminum ion. Now, if we want the concentration of our sulfate ion has a different mole ratio. So we start with our 0.232 molar aluminum sulfate. Only this time, 1 mole of aluminum sulfate is giving us 3 moles of the sulfate ion. Okay, and again, that's just going back to our reaction and looking at the 1 to 3 mole ratio. All right, so that means that our concentration of the sulfate ion is 0.696 moles per liter. So that's our sulfate concentration. Okay, and so the only difference with solution stoichiometry is that you have to pay really close attention to creating your reaction so that you have the correct mole ratio. And now that you have concentrations, you can use concentration with mole ratio. So you don't necessarily have to only use moles, although you can if you want to. So you can use moles with the mole ratio, but you can also use concentrations with the mole ratio because moles is part of the unit for concentration. And so concentrations are able to be used in conjunction with the mole ratio. That's very different from when we had mass or particles, because mass or particles can't be directly linked using mole ratio, but concentrations are able to be directly linked through the mole ratio. And the main reason for that is because moles is part of the unit for concentration. Okay, and so we're able to use mole ratio with concentration units. Okay, now there is lots of practice for solution stoichiometry Make sure that you are doing the practice. Check your answer key before you work on the check-in for solution stoichiometry.